It is the 17th of August, 1943, and somewhere over the flat marshland of northern Germany, a Lancaster bomber is climbing hard through broken cloud. Inside the fuselage, hanging from reinforced bomb racks, sits something that most of the crew have never seen before tonight. It is enormous, longer than a family saloon car, heavier than a fully loaded lorry, and shaped in a way that makes no intuitive sense to anyone who has ever looked at a bomb. The nose is not pointed, the tail fins are oddly proportioned, and when you press your hand against its casing, the metal thrums faintly, as though something inside is still settling, still waiting. The target tonight is Peenemünde, on the island of Usedom, and the men who planned this raid in the wood-paneled offices of Whitehall believe that what happens in the next few hours could determine whether London survives the next 12 months. The weapon they are carrying is the Tallboy's predecessor, the earliest expression of a revolutionary idea. That a bomb does not simply need to destroy a building. It needs to destroy the ground beneath it. It needs to reach the foundations, the tunnels, the reinforced concrete chambers that no conventional explosive has ever been able to touch. It needs to become, in effect, an earthquake. The man whose thinking lies behind this aircraft's payload is Barnes Wallis, the same engineer whose bouncing bomb had skipped across the surface of the Möhne Reservoir just 3 months earlier. But while that weapon captured the public imagination with its balletic elegance, Wallis was already moving on to something altogether more serious. He had looked at the problem of German industrial infrastructure, at the hardened bunkers and the buried fuel lines and the reinforced rocket assembly halls rising from the Baltic coast, and he had concluded that Britain was fighting with the wrong weapons entirely. Not the wrong aircraft, not the wrong crews, the wrong concept of what a bomb was supposed to do. This is the story of how that conclusion became concrete, how a set of calculations scrawled in an office in Weybridge transformed into the most technically sophisticated aerial weapons of the Second World War. And how those weapons, the Tallboy and its monstrous sibling, the Grand Slam, reached down through meters of reinforced concrete and permanently altered the trajectory of Hitler's most dangerous program of vengeance. To understand what made these weapons necessary, you need to understand what the British bombing campaign had been attempting and repeatedly failing to achieve. By 1943, RAF Bomber Command had been flying over Germany for 3 years. The crews were experienced, often extraordinarily brave, and dying at rates that would be considered catastrophic in any other context. And yet the targets that mattered most, the genuinely hardened, genuinely buried infrastructure of the German war machine, remained stubbornly intact. Conventional bombs of the period operated on a straightforward principle. They fell, they detonated on or near the surface, and they released their energy outward in a sphere of blast and fragmentation. Against wooden buildings or brick factories, this was devastatingly effective. Against reinforced concrete, it was almost useless. The Germans had known this since the early days of the war, and they had built accordingly. The submarine pens at Lorient and Saint-Nazaire, on the Atlantic coast of occupied France, were protected by concrete roofs between 3 and 8 meters thick. Bomber Command sent wave after wave of aircraft over these installations throughout 1942 and into 1943. The bombs cratered the surrounding streets, shattered the town of Saint-Nazaire almost completely, and killed a significant number of French civilians. The submarine pens themselves remained operational throughout. The V-weapon program made this problem existential. By the time British intelligence had pieced together what was being developed at Peenemünde, from the testimony of German prisoners, from the analysis of aerial reconnaissance photographs, from the extraordinary work of agents on the ground, it was clear that Hitler was investing enormous resources in a category of weapon that could not be shot down, could not be intercepted, and could not be negotiated with. The V-1 flying bomb was essentially a pilotless aircraft packed with explosives. The V-2 ballistic missile was something altogether more alarming. a rocket that climbed to the edge of space and fell on London at speeds approaching 4 times the speed of sound. There was no defense against it once launched. The only viable strategy was to prevent it from being launched at all. That meant destroying the infrastructure before it could be used. The launch sites, the fuel depots, the assembly facilities, the underground factories where the rockets were being built by forced labor under conditions of organized brutality. And those facilities were, almost universally, hardened. The Germans had seen what Bomber Command could do to an unprotected industrial site. They were not going to make that mistake with their most secret program. So the question became urgent, almost desperate. How do you destroy something that a conventional bomb cannot touch? Barnes Neville Wallis had been asking a version of this question since before the war began. Working at Vickers Armstrong's at Brooklands in Surrey, and later at their facility in Weybridge, Wallis was approaching the problem from a direction that most military planners had never considered. He was not asking how to make a bigger explosion. He was asking how to make a more precise one. Specifically, how to deliver a large explosive charge not to the surface of a target, but deep beneath it, into the geological strata below the foundations, where the energy of the explosion would have nowhere to go except upward, through the structure itself, from the inside out. He called the concept the earthquake bomb. The theory was elegant in its simplicity, even if the engineering required to realize it was anything but. If a bomb was dropped from sufficient height, Wallis calculated that this meant somewhere between 40 and 50,000 feet, altitudes that no existing British aircraft could reach. It would have accumulated enough velocity by the time it reached the ground to penetrate deeply into the earth before detonating. Not into the target itself, but into the ground beside or beneath it. The resulting explosion would not destroy the structure by blast. It would destroy it by undermining the geological stability on which it rested. The structure would not be blown apart. It would collapse inward, the ground literally pulled from beneath it. This was the theory. The practical reality required solving several problems simultaneously. The bomb casing had to be strong enough to survive striking the earth at terminal velocity without deforming or detonating prematurely. It needed to maintain its structural integrity through forces that would crumple an ordinary bomb like a tin can. The shape had to be aerodynamically stable enough that the weapon arrived at the target at a precise angle rather than tumbling or drifting, because a tumbling bomb would not penetrate the earth cleanly. And the explosive filling had to be powerful enough to generate the necessary seismic effect once the weapon had reached the correct depth. The solution to the structural problem was a casing of extraordinary thickness and quality. The Tallboy, the weapon that entered operational service first, weighed 5,440 kilograms, roughly the weight of a fully laden double-decker bus. And its casing was machined from a single casting of high-tensile steel rather than assembled from welded sections. This was not standard practice. Conventional bomb casings were welded together in sections because this was faster and cheaper. Wallis insisted on the single casting because a welded seam, subjected to the forces of earth penetration, would split. The resulting manufacturing process was extraordinarily demanding. The castings were produced primarily by Thomas Firth and John Brown in Sheffield, and the rejection rate was significant. A single flaw in the casting, a bubble in the steel, and the entire piece was scrapped. Each Tallboy represented weeks of skilled work by some of Britain's most experienced metallurgists. The aerodynamic problem was solved through the tail fins, which were offset slightly from the bomb's center line. This gave the weapon a slow rotation in flight, roughly 1 revolution per second by the time it reached the target, which acted as a gyroscopic stabilizer, ensuring that it arrived nose first at the precise angle Wallis had calculated. The rotation also minimized the risk of the weapon drifting off course in crosswinds. The fins themselves were distinctive, swept back at an unusual angle that gave the Tallboy its immediately recognizable silhouette. Nothing else in any Air Force's inventory looked quite like it. The explosive filling was Torpex, a mixture of RDX, TNT, and aluminium powder that delivered roughly 50% more destructive energy than TNT alone. The Tallboy contained 2,350 kilograms of it, detonated by a fuse that was set to fire after a delay measured in fractions of a second. Long enough for the weapon to reach its optimal depth beneath the surface, but not so long that it simply buried itself harmlessly. Production numbers remain partially classified even now, but estimates suggest that just over 800 Tallboys were dropped operationally. Its larger sibling, the Grand Slam, weighed 9,979 kilograms, 10 tons, and required the Lancaster bomber to be stripped of almost all defensive armament simply to carry it. Fewer than 250 Grand Slams were dropped in anger, each one representing a considerable fraction of Britain's manufacturing capacity for high-precision ordnance. The Tallboy's first genuine operational test came on the 8th of June 1944, 2 days after the Normandy landings, when 617 Squadron, the Dambusters, attacked the Saumur railway tunnel in the Loire Valley. German armored units were attempting to move north toward the beachhead through this tunnel, and conventional bombing had been unable to close it. A single Tallboy, dropped from high altitude, penetrated the hillside above the tunnel and detonated within it, collapsing a section of roof and blocking it completely. The disruption to German reinforcement movements in the critical days following the landings was significant. The campaign against V-weapon infrastructure that followed demonstrated the weapon's particular genius. The launch sites and assembly facilities being constructed across northern France and the Low Countries were built from reinforced concrete specifically because the Germans expected air attack. At Wharton, in the Pas-de-Calais, a massive bunker complex was being constructed to serve as a V-2 launch facility. Conventional bombing had damaged the site, but not disabled it. A raid by 617 Squadron using Tallboys in July 1944 produced craters of such depth and diameter that the surrounding ground effectively liquefied. The foundations of the bunker complex shifted. Walls cracked. The entire structure became unusable not because it had been hit directly, but because the earth beneath it had been destabilized, exactly as Wallis had theorized 5 years earlier. If you're finding this interesting, a quick subscribe helps more than you know. At Wizards, another enormous V-weapon facility built into a chalk hillside, Tallboys produced similar results. The structure itself was largely intact after the raids, but the chalk around and beneath it had been so thoroughly disrupted by near-miss earthquake detonations that the internal spaces were inaccessible. Water poured in through new fissures. Structural supports shifted. The facility was abandoned. The psychological effect on German engineers and construction workers at these sites was, by all accounts, considerable. Conventional bombing they understood and had prepared for. This was something different. Bombs that arrived with so little warning, falling from such extreme altitudes that the characteristic sound of the aircraft was often not audible until after impact, and whose effects seemed to emerge from the ground itself, rather than the sky. The German response to the problem of hardened targets followed a fundamentally different logic, and the contrast illuminates precisely why the British approach was so significant. The Luftwaffe's equivalent program produced the Fritz X, a radio-guided glide bomb that achieved notable successes, most famously sinking the Italian battleship Roma in September 1943 with 2 direct hits. The Fritz X was a precision weapon in a sense that no Allied bomb of the period could match. It could be steered by a bombardier in the parent aircraft onto a moving target, but it weighed only 1,362 kilograms, less than a quarter of the Tallboy's mass, and it operated on entirely different principles. It was designed to penetrate the armored deck of a warship through kinetic energy and then detonate inside. It had no earthquake effect. It could not undermine foundations. Against reinforced concrete infrastructure on land, it was no more effective than conventional bombs of similar weight. The Americans pursued their own solutions to the hardened target problem, developing the T-12 Cloudmaker, a weapon broadly comparable in concept to the Grand Slam, but entering service too late to see significant use. American bombing strategy in the European theater tended toward saturation, the massed application of conventional bombs across a wide area, rather than the precision penetration that Wallis had designed for. The results were often visually dramatic and materially significant, but the hardened infrastructure of the V-weapon program proved resistant to this approach in ways that the Tallboy and Grand Slam were not. There is a telling statistic in this comparison. The RAF expended fewer than 900 Tallboys and Grand Slams against V-weapon infrastructure, rocket assembly facilities, and hardened naval targets combined. The 8th Air Force dropped tens of thousands of conventional bombs against similar target sets in France and the Low Countries, with considerably less measurable effect on those specific categories of hardened target. The arithmetic is not straightforward. Different targets, different missions, different strategic contexts, but the direction of the comparison is clear enough. The legacy of the earthquake bomb program extends well beyond the specific targets it destroyed. Wallis's central insight, that the vulnerability of a hardened structure lies not in its surface, but in its relationship with the ground, became foundational to post-war weapons development. The penetrating munitions that are now standard across most advanced air forces, from the American BLU-109 bunker buster to the British Storm Shadow cruise missiles penetrating warhead, trace their conceptual lineage directly to the calculations Wallis made in his Weybridge office in the late 1930s. The V-weapon program itself was not ended by the Tallboy and Grand Slam campaign alone. The overrunning of launch sites by Allied ground forces as they advanced across France and Belgium was equally decisive, possibly more so. But the destruction or permanent disabling of the major hardened facilities, Watten, Wissens, Mimoyex, where a long-range gun installation capable of shelling London was being constructed, denied the Germans the infrastructure they needed to mount the sustained, large-scale rocket offensive that had been planned. The V2 campaign that did take place, launching from mobile platforms in Holland, killed roughly 9,000 people in London and Antwerp. The campaign from hardened, permanent facilities might have been considerably worse. Surviving examples of both weapons can be seen at the RAF Museum at Hendon in North London, where a Tallboy sits in the Milestones of Flight Gallery alongside other artifacts of the bomber campaign. Its size is striking in person in a way that photographs do not quite capture. It is simply not what the mind's eye produces when the word bomb is used. It looks more like a section of industrial pipe or perhaps a boiler. Only the machined precision of the casing and the distinctive swept tail fins suggest what it actually was. Return, then, to that Lancaster over northern Germany on the night of the 17th of August, 1943. The Peenemünde raid did not use Tallboys. The weapon was not yet in service, but it represented the same recognition that had driven Wallis's calculations. Someone, somewhere, had understood that the conventional tools of aerial bombardment were insufficient for what was coming, that the rockets being assembled on that Baltic island represented a genuinely new category of threat, one that demanded a genuinely new category of response. What Wallis gave Britain was precisely that. Not just a bigger bomb, though the Grand Slam was certainly that. Not just a more powerful explosive, though the Torpex filling was formidable. What he gave the RAF was a weapon that operated according to a different theory of destruction entirely. One that did not compete with hardened concrete on its own terms and try to blast through it, but instead reached beneath it, into the earth itself, and removed the conditions under which it could stand. The facilities at Watten did not simply have their roofs blown off. They sank. The chalk at Wissens did not simply crack. It shifted, fundamentally and permanently, in ways that no amount of repair could address. The reinforced concrete that the German engineers had specified to withstand any conceivable air attack remained in many cases largely intact. The ground beneath it did not. This is the thing that makes the earthquake bomb program genuinely remarkable and genuinely difficult to place within the standard narrative of the Second World War's air campaign. It did not succeed through overwhelming force or through attrition or through the destruction of cities. It succeeded through insight, through a single engineer's correct analysis of a problem that everyone else was solving incorrectly, and through the industrial and operational capacity to turn that analysis into reality against every bureaucratic and technical obstacle imaginable. Wallis submitted his initial proposals for deep penetration bombing to the Air Ministry in 1941. He was told the idea was impractical. He submitted revised proposals. He was told the manufacturing challenges were insurmountable. He persisted. He refined his calculations. He built scale models. He conducted tests at the Building Research Station at Garston, and eventually the mathematics became undeniable. By the summer of 1944, the weapon he had conceived was collapsing the foundations of Hitler's most secret program. The Germans built walls of concrete 4 meters thick and believed themselves protected. They were not wrong about the concrete. They were wrong about the ground. If you liked my video, please share your opinion in the comments box and subscribe to the channel. Also, turn on the bell icon so that the latest videos like this keep reaching you. See you in the next video. Take care and goodbye.